All right, Math 136 students, this is the remainder of those problems we skipped during the Thursday week 5 notes. Just wanted to make sure you have all of them filled in. Remember our exam on the material we covered this week currently and the week before is going to be next Thursday. So you'll want to make sure you watch this video completely, get your notes filled in, and start studying for that test. So this is graphing polynomials, and we learned that there's a couple of things that we want to know about when we graph a polynomial. So the first thing we want to know about is called the end behavior, and the second thing we'll want to know about is our behavior at our zeros. So for end behavior, you need to know if your leading coefficient is positive or negative, and if your overall degree is even or odd. Remember, we learned that there's different end behaviors related to these situations. So my leading coefficient is a negative, since there's a negative 1/8 out front. And then each of these, if we FOILed this out, this is a 1 power, a 1 power, and a 1 power. So all of these are x to the first. So if we multiplied all that out, it would be x to the third, which means this is an odd degree overall for the highest power. So if you are odd, you have end behaviors that head in opposite directions, and if it's negative, it's opposite to the normal x cubed. So it's up on the left and down on the right. To get your behavior at your zeros, you need to first of all set each of these factors equal to 0 and get what they solve for. So we have a -4 and a 2 and a 6. I like to put those in order from least to greatest, so that's how I've written them here. I want to know the multiplicity of each one, and I'm going to write that as a word. Now, each of these factors only occurred one time, so our multiplicity is 1 for all three of them. And that means that at that part, our behavior is that we're going to cross like a line, since all of them have a power of 1 on their factor. So we're going to plot -4, 2, and 6. Put our end behavior down first, so then this is up on this leftmost point, down on the rightmost point. And then we follow this direction. At -4, we're supposed to cross like a line. We'll keep going. And again, ignore the y values. Those are usually missing when we graph these on the test. And then we get to 2, and we're supposed to cross like a line. And at 6, we also cross like a line. So there is the graph for C. So, and again, like I said, you could find the y-intercept. I didn't graph it specifically because on the exam we give you a graph that doesn't really have the y values labeled. So the other one that we skipped in class was example E. So let's look at that one. So E has, and if I was going to start off, I'd do my end behavior first. So the leading coefficient is negative. The degree is the highest power, which is even, since it's 4. So that means that we are going in the same direction, and negative means they are both going down. So then I would factor this to find my zero behavior. So this is -1, I would pull out x to the 4th minus 12x squared plus 27. That factors into x squared minus 9 and x squared minus 3. This would factor again into x plus 3, x minus 3. This one does not factor, but we can set it equal to 0 and solve it to find our zeros. And it's going to be plus or minus the square root of 3. So we have 4 zeros here. So if we make our zero chart for their multiplicities and their behavior, we have -3 from the x plus 3. We have a negative square root of 3. We have a positive square root of 3 and a 3. Each multiplicity only occurs once per factor. Even though this is a 2 here, each of these factors occurs once because we took the square root to get the x. And so that means all of our behaviors cross like a line. Okay, so this one's a little different when we graph it. So you have to plot -3. Square root of 3 is about 1.7, so -1.7, positive 1.7, and 3. We're supposed to be down on the left and down on the right because of our end behavior. And then we're supposed to cross like a line, so that means we will cross at each x-intercept. So you get like an M shape on this one. Okay, moving on beyond the graphing polynomials, some of the other things that we talked about in class, but we didn't get a chance to do all the examples, was long division. We had a couple of those left. And synthetic division. And then we had the big problems with finding the zeros of polynomial functions. So let's do this this was part B on the long division question. So let's set up our long division. This is 2x squared plus x going into, and we need to make sure we're not missing any powers, 3x cubed minus 5x squared minus 4x minus 8. Okay, this is a harder one for us to deal with, and that's why I put it in the notes, because 2 does not just magically multiply to make 3. We know we need an x because we need to multiply by x to make an x to the third. So when you're trying to make 2 turn into 3 by multiplication, if it doesn't work naturally, you're going to have to use fraction of some kind. So what we want is we want the 2 to cancel out, and we want to be left with a 3. So we're going to need to multiply by 3 halves x. So we multiply that by everything out front. So that would be 3x cubed plus 3 halves x squared. We'll want to change all of our signs because we're doing long division before we do the subtraction step. So this should cancel. You'll need to make that negative 10 over 2 to have a common denominator. So negative 10 over 2 minus 3 over 2 is negative 13 halves x squared. Bring down the minus 4x and the minus 8. So the next question is, what do you multiply 2x squared by to make negative 13 over 2x squared? So again, the x squared is fine. We don't need an x this time, but we need to figure out how to times 2 by something and make negative 13 over 2. So we know we need a negative sign, and we want the top to be a 13. The problem is we don't want the 2 to cancel out with a 2 in the bottom. We want to have a 2 in the bottom left over. So we need to know what number would you put in the bottom to make it reduce to a 2. And the answer to that is 4. So 2 and 4 would reduce and leave a 2 in the bottom. So we're going to multiply this up top, or put up top a negative 13 over 4. No x needed since the x's match. And we multiply that by everything out front. And that would be negative 13 over 4x. We'll need to change our signs before we do our combining step. This would be negative 16 over 4 if we write that as a common denominator. So that is negative 3 over 4x minus 8. You cannot go another round because 2x squared is bigger than the x to the first, so we are done. So my quotient here is 3 halves x minus 13 over 4. My remainder is negative 3/4 x minus 8. So that one is just a little bit trickier than the one we did in class because of the fractional parts. Now, for C, this is a question just to see if you realize when or can we multiply and when can we not. If you notice, this is an x cubed that's trying to go into something that is x squared, and we do have a missing term there. You have missing terms out front too, but it's crucial that you get the ones that are inside. These don't really affect anything. So this would be, you can't put it in at all. So my quotient is 0, and my remainder would just be what's inside because we can't do anything with it. And we would obviously put that over the divisor if we were writing it as a division algorithm, but essentially we cannot do the division. Okay, so let's talk about synthetic division for a minute, because we had a couple problems left over from that section. We learned about the remainder and factor theorem. We did one synthetic division problem on this first set of examples. I left B part for us to do on a video. So the directions above said use synthetic division to find the quotient and the remainder of the first polynomial is divided by the second one. So remember, the first step is to make sure this is already solved for its 0, so that's x equals 3. You put that in your box. You have to make sure you're not missing any powers. So we have negative 2, we're missing the x cubed, we're missing the x squared, we have our 10 and our negative 3. Pull down the negative 2. This is negative 6 when we multiply. Add that. That's negative 18. Multiply, that's going to be negative 54, which is negative 44. And I think we did this one in class, which is fine. And then this is negative 132. When you do 3 times negative 44, for negative 135. So remember, your quotient is the part that's in front of this remainder box right here, and it's always 1 power less than what you started with. So it's negative 2x to the third minus 6x squared minus 18x minus 44 with a remainder of negative 135. And remember, we can only do synthetic division if we're dividing by an x to the first power. So example 4, we're showing that we can do this with, if they've already solved it for us. So essentially this one's already been solved. It used to be c minus a half. So we'll put the 1/2 in there. We have an 8. We're missing the 4th power. We're missing the 3rd power. We have our x to the 2nd power. We're missing the x to the 1st power, and we have a 7. Pull down the 8. Half of 8 is 4. Add the column. Half of 4 is 2. Add the column. Half of 2 is 1. Add the column. Half of negative 2 is negative 1. Add the column. Then we get a negative 1/2, which means we get 6.5 in this last part, which we would write as, this would be 14, so 13 halves. So this is now it just says find f of c. So f of 1/2 is this remainder. That is 13 over 2. Now if they asked us to find the quotient and the remainder, obviously we could write that as well. And then the 5th example says prove that this is a 0 of f of x. So if you do synthetic division and you get 0 as a remainder, that means that this would have been like x minus 3 if we solved it back over. That factor goes evenly into this polynomial. So we have our 3. We're missing power. No, we're not. So this is negative 9, negative 8, and negative 3. Pull down the first coefficient, multiply, add the column, multiply, add the column, multiply, and we get a remainder of 0. If the remainder of x equals 3 into is 0, then x minus 3 is a factor of f of x. Okay, so that gets us into the discussion on the rational zero or root theorem. We learned about that last time in class, about the list of p's over q's. And what we want to do with this is, there was a couple of things I skipped before the very last problem. We did not do example 9 or example 8. So let's do those really quick. This one is, express this as a product of linear factors. Linear factors means every single factor has to be an x to the first plus or minus something. That's what we mean by linear. Okay. And find the zeros of f of x. So the first thing I would notice is I can pull out an x cubed, and that leaves me with an x squared minus 4x plus 13. Unfortunately, that quadratic doesn't factor any further, so we need to use quadratic formula to break this up into linear factors, because right now this is a quadratic factor. By the way, this one can be written as x minus 0 to the third. That way you can see the 0 answer. So we want to know if we can factor this at all. So x equals negative b plus or minus square root. B squared would be 16 minus 4ac all over 2a. That's 4 plus or minus the square root of, let's see, that's 16 minus 654. So that's, no, 52. So 16 minus 52 is going to be negative 36 over 2. So that's going to be an I problem. So that's a 6i over 2. So this is 2 plus or minus 3i. Now, when writing something as a factor, I'm going to show you the zeros over here. So one of my zeros is 0, and it had a multiplicity of 3, by the way, because it occurs 3 times because of the cubing. My other factor, one of them is 2 plus 3i, and the other one is 2 minus 3i. So this is the zeros. So that's one part that they asked us for. To turn these back into factors, you need to solve it back equal to 0 in each of them. So we need to subtract 2 and 3i to the left side. And here we will subtract 2 but add 3i. So that's what they look like when they're factored using imaginary solutions. And since they said they wanted this factored linearly, and they didn't specify that we could only use real numbers, because they usually will if they want you to only use real numbers, then this is actually the complete factorization. Okay, let's talk about example 9, which is that we are going to be expressing the polynomial given as a product of linear and quadratics that have real coefficients and are irreducible over the reals. So in other words, it's okay to leave a quadratic in your final answer as long as it's not going to work by normal factoring. If it's going to solve using quadratic formula or completing the square, then we would want to use that when we do linear factors. So let's look at the first part. We'll pull out, looks like 4 terms, so we're going to do GCF. So x to the third out of the first pair. That leaves me with x squared minus 4. Positive 1 out of the second pair. That also leaves me with x squared minus 4. We have a match of x squared minus 4 and x cubed plus 1 is the leftovers. That gives me an x plus 2, x minus 2. And then this is perfect cube, so it factors into a cubed root of x cubed, which is x, cubed root of 1, which is 1. We keep our signs. But then remember, there is a trinomial. So the first times the first would be x times x, so that's x squared. First times second is 1x. Second times second is 1. And then remember, we remembered SOAP to get our signs. So same as the original, opposite to the original, always positive. So this part broke into those, and this part broke into those. So this is the answer for writing that factored over what we call the real numbers. So it's mostly linear little factors, but the quadratic is not one that factors normally. So then we would want to factor this last part using imaginary or radical solutions that don't reduce by using quadratic formula. So this one is x equals negative b plus or minus square root b squared minus 4ac all over 2a. This is 1 plus or minus the square root of negative 3 over 2. So since this is going to have an I, we're going to split it up. So it's 1/2 plus or minus square root of 3 over 2i. So remember, if we're going to turn those into factors, imagine writing them out and solving everything back over to the left. So minus 1/2 minus square root of 3 over 2i. The other one will be x minus 1/2 plus square root of 3 over 2i. So we're going to replace that trinomial at the end with those two factors. So we have x plus 2, x minus 2, x plus 1, x minus 1/2 minus square root of 3 over 2i, and x, running out of room, minus 1/2 plus square root of 3 over 2i. So this is the factored over the complex numbers instead of just real numbers. Okay, and then the very last one we have left is the 4th degree. Solve this by the rational root theorem. So your first step is to locate the factors of p and the factors of q, which is our constant and our leading coefficient. So the factors of p is, and we always put plus or minus because we don't know how they came up with this negative, how they did their signs, except they're opposite signs. So we have 1, 2, 4, and 8. The factors of q are plus or minus the factors of 3, which are 1 and 3. Now that is not our list, that's just the individual factors. What we're going to try in synthetic division or the remainder or factor theorem to figure out our zeros is we're going to use the p over q list. So 1 over 1 is 1, 2 over 1, 4 over 1, 8 over 1. 1 over 3, 2 over 3, 4 over 3, 8 over 3. I typically start with 1 and -1. This will be what we call round 1. Since this is a 4th degree, you're going to have to go through 2 rounds to get down to x squared so that you can use quadratic formula. So I always start out with +1 and -1. So this would be, let's get our coefficients lined up. We're not missing any powers. So there's a 3, a 14, a 14, a -8, and a -8. Pull down the 3, multiply, that's 3, add, it's 17. Multiply, add, that's 31, multiply, and that's going to be 23, and then multiply, we get a remainder of 15. So not 0, so 1 does not work. Then we do -1, so 3, 14, 14, -8, -8. That is -3, so that's 11. That'd be -11, so that'd be 3. -3, that's -11. And +11, which gives me a remainder of 3. So even though neither one of these worked, the negative was closer to a remainder of 0. So I'm going to try -2 next. So that is still going into my original polynomial. So we bring down the 3. That's -6. That's 8. Multiply. It's -2. Multiply. -4. And multiply. And we get a 0. Yay! So that's good. So right away, you want to go over to your answer key, wherever that may be, and write that x equals -2 is a solution. Now, what's left is going to be a reduced polynomial. So this is going to be round 2. So this was x to the 4th. So now we have 3x to the 3rd plus 8x squared minus 2x minus 4. It is also good to reevaluate your P over Q list for this second round. If plus or minus 1 failed in the first round, it's still going to fail. We will immediately try -2 again, because sometimes the answer occurs more than once. It's a multiplicity. We have a 4 still, but we no longer have a factor of 8. This has got factors of 4 are just 1, 2, 3, or 1, 2, and 4. So 8 is out because it's no longer in the new P over Q list. 1/3 would still be in, 2/3, and 4/3. So the 8 over 3 and the 8 no longer apply to this reduced polynomial. Okay, so I'm immediately going to start with -2 just because that's a good place to check to make sure there's no multiplicity for that number. So this is a 3, that's -6, that's 8. It's -16, that's -2. That's 4, that's -4. That is 8. Oops, I did it in the wrong one, sorry. I knew that didn't look right. This one's not supposed to have a multiplicity, and this is why. When you go to do round 2, you have to use your new polynomial. So it's -2, and then it's 3, 8, -2, and -4. Sorry about that. I was looking at the black line. You have to use your new polynomial in here. Otherwise, you're never going to get anywhere. So this is 3, so that's -6, that's 2, that's -4, that's -6, that's 12, and that is 8. So notice my remainder does not come out to 0 again. That doesn't mean it didn't work the first time. It just means there's no multiplicity. -2 is a singular answer. It does not occur more than once. So what I would try next is maybe +2 to see how crazy off that might be, since this was close to 0 but not super close. So that's 3, 8, -2, -4. That would be 6, and then 14, multiply. That is 28. That's 26. That's 52, and that's 48. That's even worse. That's much farther away from 0. So usually when this happens, I jump in and try a few fractions. It doesn't hurt anything. So let's try maybe 2/3, because that's sort of in the middle of my group. So this is 3, 8, -2, -4. Pull down the 3. That's going to be a 2. That'll be 10. And then this is where it starts to fall apart, because that's 20 over 3 when you multiply, which means I have to make this guy also have a common denominator. So -6 over 3 and 20 over 3 is 14 over 3. And then my remainder column is going to be multiplying these guys together, 2/3 and 14/3. So that is 28 over 4. So this would be -20, let's see, no, -16 over 4, if we make it a common denominator. So 28 minus 16 is 12 over 4, which is 3. So again, not a great remainder, but it is closer than 8 and 48. So let's try the negative of 2/3, because sometimes just changing that sign helps you out. So this would be a -2. That makes a 6. That would be -12 divided by 3, so that's -4. That makes a -6. That'll be +12 divided by 3, which is a 4. And there's another 0 for us. So we want to go up to our blank where we would have our answer, and we would write -2/3 next to the -2. Now it's up to us to find the last two solutions, and you don't need to keep doing synthetic division. First of all, you're not guaranteed that they are rational roots. They may be radicals or imaginaries. So this 3x squared plus 6x minus 6 is what we're working on now. So I can divide everything by 3, and that would make it x squared plus 2x minus 2 equal to 0. So x equals negative b plus or minus square root. B squared is 4 minus 4ac, sorry, I'm running out of room, all over 2a. So I ended up getting negative 2 plus or minus the square root of 12 all over 2. And square root of 12 is a 2 on the square root of 3. So I'm going to write this up here. So from the quadratic formula, we got negative 2 plus or minus 2 on the square root of 3 all over 2. And then we reduce all the 2's on the outside. So it's just negative 1 plus or minus the square root of 3. So that is all for solutions to that polynomial. Okay, so the big deal between like a third degree and a fourth degree is just how many times you have to go through the synthetic division. If it was a fourth degree, you will have to go through 2 rounds before you can get to a quadratic, whereas if it's x cubed, you can get to the quadratic after 1 round of synthetic division. So just make sure you guys go through this and let me know if you have any questions at all.